So now in our previous example, we saw that the velocity with respect to time equals now this is the velocity of the falling object, is equal to the gravitational acceleration multiplied by the mass of the object divided by our drag coefficient, and this all multiplied by an exponential form. Now this equation represents an analytical or an exact solution. And the reason why we call it this is because it satisfies the original ordinary differential equation. But unfortunately, this is not always possible. As engineers, we have to develop a new method to solve complex ordinary differential, partial differential equations. And this alternative method is what we call the numerical solution. And the numerical solution approximates the exact solution of the PDE. But now this requires reformulation. And we're going to try and visualize that from our previous problem. It's a falling parcel in Newton's second law. So again, if you recall, the acceleration is some function of the force applied, the resultant force applied to the object divided by its mass. We know that acceleration is the time rate of change of velocity, dv dt. And this in turn can be written as delta v delta t. So the difference of the velocity with respect to the difference in time. So we can again rewrite this as the velocity at some time t plus 1 minus the velocity at the current time divided by t at some time in the future minus current time. Now, Vt is our initial velocity. The velocity at t plus 1 is what we call the velocity at some other time, or the time of the future. Denominator represents our step size, or the difference in time. Now, the reason why we can approximate the derivative of the velocity with respect to time as delta v delta t is because delta t is finite. And if you remember from calculus, if delta t is finite, then the derivative of the velocity with respect to time equals the limit as delta t approaches 0 of dv dt. So we can apply this now to our analytical solution, and we can approximate the acceleration as the velocity at some time t plus 1 minus velocity at the current time step divided by t plus 1 minus the current time. And this is equal to gravity minus c of m v at the current time. Now if we jumble our terms around, we can get that the velocity at the next time step equals the velocity of the current time step plus g minus c over m, velocity at the current time, multiplied by t I plus 1 minus t I. Now, hopefully, this looks like something you've seen before. Here we have the new value of the velocity, and it's equal to the old value plus some constant multiplied by a delta t. Now this represents a simple linear equation where the new value equals the old value plus the slope multiplied by your step size. And this is formally called Euler's method. Now let's apply that to our falling parcel in the next exercise.